We're ready for the next talk. This talk's going to be about operator fusion. Those of us who program GPUs love fusion, and this is a way how to do a really good job of it. So Yifan from UIUC, take it away.
Yes, thank you for the introduction. So that was a little bit of interruption, right? So from the fire alarm, let's use some power from the sea to stop that. I introduce you Neptune. I'm Yifan from Illinois. This is my work, and I will tell you a story of how breaking the program and fixing it can bring us better operator fusion and better compilers. So Neptune is a deep learning compiler. The task of a DL compiler is to take a DNN and compile it to the hardware with good runtime performance. DNN here can be CNNs, LSTMs, large language models. Many large language models today are built on the attention mechanism, which turns out to be an interesting case for deep learning compilers. So let's pay some attention to attention. Mathematically, attention is simple. Two matmos, a softmax, some element-wise operation. You can describe what attention does in like 5 lines of code. Implementation-wise, that got ugly. Kernel engineers write this instead, goes on for a few screens to get serious performance. So the gap between the math and the kernel you have to write today indicates that something is missing. Attention escapes compilers today. Compilers today cannot start from the simple math and produce a kernel with the performance that matches your manually implemented ones. So in the case of attention, we can actually pinpoint a main reason for that. The compilers cannot figure out an important type of optimization, and that is flash attention. Flash attention provides an alternative computation order for attention. So instead of fully calculating matmul 1, then softmax, matmul 2, flash attention does one tile of matmul 1, one tile softmax, one tile matmul 2, and move on to the next tile for the entire program, and so on. That means smaller tiles of data fitting on the faster but smaller caches of devices like GPU SRAM, the memory overhead decreases, and flash attention runs faster. Well, that rang a bell, didn't it? That is operator fusion, both in terms of the benefit and the pattern. And operator fusion is a classic optimization. Many existing compilers can already do that, except they all fail on attention because there is more data dependency in attention. To be specific, that means reductions in the softmax and matmul that is beyond what classic operator fusion algorithms can do. Neptune fixes that problem. In Neptune, we invent a more powerful, novel type of fusion. We simply call that advanced operator fusion, and closes the gap between the math and the kernel. And Neptune advanced fusion does not just work for attention. It generalizes to a class of different programs. In this process, we find out that there are many programs waiting to be fused in this way that today's compilers cannot. And in Neptune, we finally have the right tool to do this natively, automatically, within a compiler. So advanced fusion, that is the first main contribution of Neptune. The way advanced fusion works, as I promised, this is a story of breaking then fixing the program. We implement that idea in 2 variations. Both compiler passes are general over different programs. If you apply them back to our attention example, you get familiar results. Applying rolling update to attention gives you flash attention. Applying the other variant, what we call split K update, gives you a structure like flash decoding. And there's more. Neptune has a special design where the optimization pipeline is 2-staged. There is a loop IR, which is the higher level IR for high-level optimizations, just like our advanced fusion. And there is a tile IR on the bottom that is for the more hardware-specific optimizations. This is perhaps easier to see in a full system view of Neptune. Advanced fusion work on loop programs. It is in the loop optimizer as well as many other loop transformations. Then in the second stage, Neptune actually uses existing tile compilers like Triton to perform highly hardware-specific optimizations. Neptune's own tile IR, we have one, easily maps to the input language of the tile optimizers, and these 2 stages are connected by a translator that converts loop to tile via tensorization. There are 2 inputs to the entire system of Neptune: the definition of the operator and a small high-level schedule template that is for the loop optimizer. The schedule template can invoke transformations available in the optimizer, such as our rolling update fusion. This idea is similar to the algorithm schedule split in existing schedule-based compilers like TVM, if you are familiar with that, except Neptune's schedule is much more concise because a lot of optimization steps would be downstream and automated in the tile optimizer. Here is an example program in Neptune's loop IR. This program has 2 loop nests. The first one is a reduction. It runs over a 2-dimensional input and gives you the per row max, which is the vector here. And the second loop nest is an element-wise operation between the input and xmax to give you a 2D result of xexp. Now, this example also shows, well, it's a simplified case, but it shows why flash attention style fusion is difficult. We are essentially asking to fuse the second loop nest under the reduction loop of the first nest. Here, that will be the J loop. If you force the classic operator fusion to do that, you get a program that is incorrect. And to see why it is incorrect, check this out. That's the input. That's the data dependency diagram of the original program where we calculate xmax first before moving on to xexp. And in the incorrectly fused program, the data dependency is changed. So because everything is under the J loop, we are calculating xmax and xexp simultaneously. We are essentially reading from xmax too early before it finishes. Compiler textbooks say this is a violation of temporal data dependency. Today's tensor compilers say this fusion is illegal and will reject it. In Neptune, we say we do the wrong fusion anyways. Break the program, then we change the computation in the program to fix the result, which is now something classic fusion cannot do. Let's use a slightly longer example. Our previous one adding a row-wise sum at the end, so we have 2 reductions. This is, by the way, similar to softmax. Neptune sees this program. It first applies the wrong fusion, which gives us this program on the right-hand side. Next, we find the fix for the program. We don't apply it on the first reduction. We don't apply it on the element-wise operation. The fix happens to the second reduction, where instead of taking a normal sum, you are multiplying the current sum with this term here to fix the result. That is what we call the repair term. And the key insight of Neptune fusion is finding the right repair term and adding that at the right place gives us a program that is correct again. So how do we find this repair term? Neptune has an algorithm for automatically doing this for general programs, and we have proof for its correctness. The margin here is unfortunately too small for the proof. In our paper, we have like 5 pages of proof and derivation to show how to do this and why it's correct. Here, instead of saying the proof, I'm going to give you an intuition of why Neptune fusion generalizes. So let's look back to our fused example program. This program says a few things about the computation in one place. There is the loop structure. And within the loop, there are a bunch of scalar expressions doing the computation with some data dependency. Now, the loop structure is already good thanks to our naive fusion. So we want to turn to the next thing, that is the data dependency described here, which says we have a pair of reduction and an element-wise operation in between, and both the first reduction and the element-wise read from the input array. Well, by the way, Neptune can easily deal with more complex data flow, and that is treated in the paper. Back to our example with the loops dropped. Now, the next thing we want to figure out is what kind of computation is being done, and we want to describe it in a way that is independent from the data dependence. And that means we want to extract the scalar expressions we are using for the computation. For the first reduction, it's simple. It's the max operator. And perhaps surprisingly, Neptune doesn't really care much about what's being done in the first reduction, the computation. But we do care that in the element-wise operation, we are reading from the first reduction as well as non-reduction inputs. So we want to label them separately. We can call them R and C, and that gives us an expression G of R and C, which is exp C minus R. And we can do the same thing to the second reduction. Because it's a summation, we can get just X plus Y. The reason why this is important is now it allows the Neptune repair term algorithm to only look at scalar expressions. So F and G are expressions as inputs to the algorithm, and it gives you a repair term also as a scalar expression automatically. This is essentially a symbolic solver, and it's built on SymPy in Python. And this is why Neptune Fusion can automatically apply to many different programs. We have applied it to not just softmax, attention, but also L2 norm, RMS norm, and performer. And in many cases, we observe significant performance gain. For example, here in L2 norm, we are getting like up to 6 times performance benefit just from the fusion. We will see more of that in the evaluation. Now, briefly on the other variance, which is the split K update. So in rolling update, everything is under the same loop nest, and the repair term is here. In split K update, the loop structure is different. We want to create 2 loop nests. The goal is this. We want the first loop nest to be fully parallelizable. It runs local reductions. And then the second loop nest is where we change the computation to fix the result. So this gives us a different trade-off point compared to rolling update. You get more parallelism at the cost of a little bit of data stored in addition. Back to the full pipeline, a few words on this because there's an interesting design decision I wanted to show you. But before that, let's see how loop and tile programs can work together in the same pipeline. Just to make things even simpler, this is a matmod in Neptune's language. So when the program comes in, first it runs into the loop optimizer, which does multiple things like tiling and parallelization, which gives you a program like this on the bottom, which is optimized by the loop optimizer. And then next, what happens is the loop to tile translator will latch onto the inner loops of this loop structure, as well as the compute statement, and translate entire of that into one tile statement. So now we are in tile IR category. And then you can see there is a clear separation of obligation between the loop and tile optimizer. The loop optimizer created the outer loop structure, and now it is time for the tile optimizers to take on the dot product and optimize it. And it turns out tile languages are quite good at that, at optimizing these tile dot products, for example. So tile languages like Triton, TileLang, there are many more of them. They are good at automating some low-level optimizations, like if you write a dot product, it will automatically figure out how to use tensor core product for you. But that doesn't mean writing kernels in tile languages is easy. You will still need to figure out all of these low-level optimizations, as well as high-level optimizations like the advanced flash attention style fusion we just saw. And then you put all of that knowledge into the tile code you end up writing. So the position we take in Neptune is we want programmers to start from mathematical expressions, not write tile language tile kernels, but then we want the compiler to be able to bring the mathematical expression all the way down to CUDA heap level of performance on the hardware. And that is asking a lot of the compiler, so we want to get all the helps we can get, including reusing existing tile compilers for our pipeline. That is why we made this design decision. Now let's see how effective Neptune is with its design. We have evaluated Neptune on 10 different variants of attention, 6 prefill, 4 in decode, as well as non-attention operators like these 3 I mentioned earlier. And for each of them, I vary the input shape, such as the sequence length of the input. And for each of these setups, I also evaluate them on different GPUs, including 1 AMD GPU and 3 NVIDIA GPUs. So this is how we show our performance. How do we read this? Well, this is one setup on the NVIDIA A100 GPU with causal prefill attention operator. And we are varying the sequence length on the x-axis. On the y-axis, that's the performance. Higher is better, and it's all normalized relative to Neptune. So that's why Neptune is this green line here that always stay at 1.0. And you can see in this setup across all the sequence lengths, Neptune consistently outperforms all the other baselines here, including flex attention from PyTorch to Triton manually written kernels, as well as TVM, the compiler. Now let's scale this up to different GPUs and different operators. Here, 3 of the 6 prefill variance of a tension operator, and across all the 4 GPUs, you can see Neptune still has, it's the same trend, right? Neptune gives you great performance and outperforms all the other baselines in most of the cases. And the same trend holds for the decode variance. Here's 2 of these 4, and you can see the performance gain is sometimes even larger on less optimized setups like AMD GPU. And you can see that again in this summary table, the performance on AMD MI300, we are getting almost 2x of speed up compared to all the baselines on average, compared to over all these different operators, geomean average, by the way. So that's the evaluation. We have more evaluation results and more interesting details in the paper, and I encourage you to read that and figure out. What we did after the Neptune submission is we kept extending the system, and now we have an additional set of interesting results as well, including better performance on next generation GPUs such as Hopper and Blackwell as well, and I'm happy to talk about all of that after this talk. But in conclusion, data locality is critical and a difficult problem as indicated by flash attention. Neptune fixes this problem with its advanced fusion and improves locality, and Neptune loop plus tile optimization maximizes the performance. Therefore, Neptune generates high-performance code on different devices for different operators. That's the end of my talk. I'm happy to take your questions.
All right, questions?
OK, so if I understand correctly, the correction term is like a genericized version of the logic behind the online softmax correction. So in the flash session paper, they had to manually think through carefully the numerical stability implications of doing this correction. And so I'm wondering, like, do you have evaluation of that? And for this automation, how would you reason about the consequences numerically of doing this in the compiler?
I see. That is a great question. So what we have, I'll tell you what we have. We have proof of, well, correctness over real arithmetics, like you probably have guessed. That's by the way, that's basically the way Trade also did that in their flash attention. When they're proving the correctness of the repair term, they are doing that over real arithmetics, and then they reason about, well, they test the numerical accuracy on floating point numbers separately, and we did the same. So you can see here, this is also in the paper, by the way. We have a set of empirical study of the numerical precision of our kernel compared to the baselines, I mean, kernels from other baselines. And we are on par, sometimes maybe even a little bit better here compared to. Yeah, left is lower error, so that it's better. And you can find a full set of that result in our paper. So this is currently where we are at. We are empirically evaluating the numerical accuracy of the kernel, and it may be interesting future work to do this in a more analytical manner that is outside of this paper.
Great answer,
thank you.
I think we have time for one more question. I mean, we're a little bit delayed because of the fire alarm, but I just want to make sure folks have a chance to ask questions. Oh, let's go, James.
Thank you, great talk, really interesting work. So there were only 2 cases there where you lost out to other compilers, and I was wondering if you had any intuition for those results, whether you investigated why you lost out.
Oh, which cases? Sorry, just 1 second.
So I think if you go back to your average performance, yeah, there were 2 cases on there where like there's 0.99 and there's 0.95, and I was wondering if you had any, like you investigated those cases and had any intuition why you lost out.
Right, so there are a couple of reasons why, well, you can start setting up.